We are pursuing BTech in Computer Science and Engineering from Manipal University, Jaipur.
We are from Section F in the second year, going to present a case study in computer organization and architecture on RISC-V processor.
Hello everyone. Today we are going to talk about a very interesting processor called RISC-V, especially the RV64GC version. It's becoming quite popular in the tech world and we will explain why.
Yes, we'll walk you through how it works, its design, pipeline, memory, and even how it compares with other processors.
Let's talk about its architecture overview. So first, RISC-V is based on the RISC principle, which stands for Reduced Instruction Set Computer. That means it uses a small number of simple instructions that can run very fast.
Unlike CISC processors like Intel's x86, RISC-V focuses on simplicity and efficiency, and the best part is it's open source. Anyone can use it or modify it without paying license fees.
Exactly. Because of that, it's used in all kind of devices from IoT gadgets and embedded systems to AI chips and even supercomputers. The RV64GC version supports 64-bit operations and extra features like floating point atomic and compressed instructions. In Now we will talk about its instruction set architecture. Now let's talk about the instructions. All RISC-V instructions are 32 bits long, which makes them easy to decode and execute. There are few main types. R type for register operations, I type for immediate or load, S type for store, B type for branches, and J type for jumps.
And it supports simple addressing modes like immediate, register indirect, and PC relative. One cool feature is the compressed instruction set, which uses only 16 bits to save memory, perfect for smaller devices. Another is atomic instructions that help when multiple cores access the same memory. That's right. Now let's move how these instructions actually flows inside the processor.
Let's talk about its data path and pipelining. RISC-V follows a five-stage pipeline: instruction fetch, decode, execute, memory access, and write back. Each stage does one part of the job, so several instructions can be in progress at the same time. After the pipeline fills, the CPU can complete one instruction every clock cycle. That's fast. Some advanced versions of RISC-V even allow out of order of superscalar execution, meaning they can handle multiple instructions at once.
Now, next is the memory hierarchy. The memory system is also well organized. There's a small, fast L1 cache for instructions and data, then larger L2 and L3 caches, and finally the main memory.
Okay, it also supports virtual memory for operating systems and keep multiple cores in sync with cache coherence techniques. Some designs even use scratched memory to speed up real-time programs.
Now, next comes the specialized features and parallelism. RISC-V can work with multiple cores, which means it can process several tasks at the same time. It also has special vector extensions like like SIMD, which helps with AI, graphics, and machine learning work.
Plus, there are virtualization and crypto extensions for better security and performance. What makes it special is that designer can pick and choose which features they need. It's truly flexible.
Now, next comes the historical significance and comparison. Now, let's talk about where it comes from. RISC-V started at UC Berkeley in 2010. as a university project. The goal was to create a free and open processor design that anyone could study or build. If we compare it with ARM is proprietary and requires licensing. RISC-V is open and free. ARM is very mature and optimized, but RISC-V offers more customization and flexibility.
If we compare it with ARM is priority and requires licensing. RISC-V is open and free. ARM is very mature and optimized, but RISC-V offers more customization and flexibility.
So to sum up, RISC-V RV64GC is simple, flexible, and open. It can power anything from a small embedded board to a high-end AI server. It's challenging the processor world by making hardware design open to everyone.
Okay, let's talk about its code simulation. We will give you live demonstration of it and explaining what is happening in this code. So you can see this is our code and we will run it and it run very smoothly. So let's talk about its data section. In data section, we store the text message that we want to print. Message holds Fibonacci sequence, the heading. Space is just a single space used between numbers. New line moves the cursor to the next line after printing the all numbers.
Now next comes the text section and start. In the text section, we start execution at the label start. First, we print the heading using a system call li a7, 4 la a0, message msg equal. Here a7 equals to 4 means print string and a0, that is a0, holds the address of the string.
Okay, initializing Fibonacci variables. Next, we set up our first two Fibonacci numbers and the loop counter LIT0 0, LIT1 1, LIT2 10. We want 10 terms. Fibonacci loop. Inside the loop labeled fib underscore loop, we print the current number stored in T0. MV A0 T0 LI A7 1 equal. Here A7 is equal to 1 tells the system to print an integer. Then we print a space after it for neat formatting.
We calculate the next Fibonacci series term, the next term at T3, T0, T1, MV T0, T1, MV T1, T3. This updates the two numbers for the next loop. We reduce the counter, add I, T2, T2 minus 1, thence T2 fib loop. If T2 is not 0, it loops again.
Now in exit part, after printing all 10 numbers, we print a new line and exit cleanly. LI A74 LA0 new line equal LI A710 exit equal. In output, we will get 10 Fibonacci sequence and our code is run smoothly and we will show you the output of this code. You can see the output. It print all the Fibonacci sequence numbers and exited successfully. Now I sh I showing you a picture of this processor. We have a pro sample photo of this processor. You can see, and there is our presentation. And thank you. And we hope that you understand